Hello to my year nines. Welcome to lesson 3. So if you remember back to lesson 1, we learnt all about the nervous, endocrine and immune systems, and we talked about how each of them send messages in the body to maintain balance. Then last lesson we talked about feedback mechanisms. We talked about our negative feedback and our positive feedback. So today we're going to try and bring them both together and start talking about how the nervous and endocrine systems work specifically in the negative feedback mechanisms. And today we're going to talk about thermoregulation, which is our body's ability to maintain our own body temperature. Okay, so the learning intentions for today's lesson is that by the end of the lesson, you'll be able to discuss how the nervous and endocrine systems work together to maintain body temperature. And you're also going to be able to apply your understanding of negative feedback mechanisms to explain a simple example of when these mechanisms fail and what this does and how it impacts homeostasis. So again, we're going to start using our scientific language and make sure that we're sounding like scientists. So if you can't quite remember what we learnt last lesson and the first lesson, just quickly go back and revise and then come back, all right? So today we're going to start with an experiment or two. So you can either choose either one of these or you can do both. It's up to you. But the first one is a heart rate experiment. So what I want you to do is for 15 seconds, I want you to take your heart rate. Now, the way you take your heart rate is we have a nice big artery that comes along our neck here. And so we can actually feel our pulse through that. So you're going to use 2 fingers resting on your neck there, and you should be able to feel your pulse. If you can't, that's okay. You're alive. You're looking at me. You'll be okay. We might just have to find a different spot. Okay, so the other option is on your arm, in line with your thumb. If you use 2 fingers, you should be able to feel your pulse there. Now, don't press too hard because then you're actually going to push against your blood vessels and you may not be able to feel your pulse then. So just nice and gentle. Now, the reason we're doing it for 15 seconds, you're going to count how many times you feel it beating in 15 seconds, and then you're going to times it by 4 because there's 60 seconds in a minute. So, for example, for 15 seconds, you count 20 beats, all right? So you count 20. You're then going to times that by 4, and it will be 80, and that will give you your heart rate for a minute. I then want you to note that down in your notebook, and then go do 3 minutes of exercise, whatever you want, all right? It can be star jumps, it can be dancing, it can be running around in the backyard, it can be running around on the spot, do some footy, whatever you want to do for 3 minutes, and then come back and take your heart rate again for 15 seconds times by 4 and write that down. And I want you just to take note of what's different. Why is it different? And what's happening inside the body that's making that change. The other option is sensing temperature. So for this, we need 3 bowls, buckets, whatever, of water. One is going to be very cold, so straight out of the fridge. The other one's going to be warm, but absolutely not hot because we don't want to burn yourself, okay? It needs to be comfortable enough that you can keep your hand in it for 30 seconds, okay? Your left and your right hand are going to both go into the buckets of very cold and warm water at the same time for 30 seconds. Then I want you to put your both hands into the room temperature bucket for 30 seconds, and I want you to take note of what you feel in each hand and why you think you might be feeling that. We're just going to watch a quick video as of some revision for homeostasis and negative feedback mechanisms.
Feedback loop to help maintain homeostasis. Feedback loops are broken into 3 parts: the stimulus, the sensor, and the response. Let's start with this loop over here on the left. Imagine that it's a very hot day and the individual's body temperature is rising. The rising temperature is the stimulus. The stimulus is then detected by the sensor located within the individual's brain. In humans, a temperature change would be detected by the hypothalamus, but obviously Homer Simpson's brain is a little bit different. Because high temperatures can cause cell death, the body then goes into action to bring its core temperature down. Blood vessels will dilate, allowing heat to radiate outwards, and the person will also begin to sweat in order to decrease their body temperature via evaporative cooling. Hopefully, the effect of these steps will be enough to bring the person's overall body temperature back down to normal. This phenomenon is called a negative feedback loop, not because it's bad, but because it helps to make the situation less extreme. See if you can figure out what would happen on the right-hand side of the loop when the temperature got too cold rather than too hot. Ideally, if your body temperature gets too cold, You begin to shiver after detecting the decreased temperature in your hypothalamus. The shivering generates heat, which should bring your body temperature back up.
So if you remember, our negative feedback mechanisms has a stimulus, which is the temperature either going up or down. We then have the sensor, which would be the sensors in our skin or our nerve receptors, which we'll talk about. The control center in our brain, so our hypothalamus. Then it sends a message to our effector organ. So this is our veins to dilate so that they get bigger, and our sweat glands. And then the response is that our body temperature comes back down. Okay, so let's specifically talk about the nervous and the endocrine system. So we know that our body needs to stay at a pretty constant temperature. Otherwise, our body systems don't function properly. So the nervous and endocrine systems interact nicely and regulate temperature through immediate responses and hormonal adjustments. So this is a nice little picture of our nervous system. It's a bit creepy, really. But we have our central and peripheral nervous system. So we've got our brain, and then our spinal cord, and then our nerves that come off the side. Okay, so this allows for rapid transmissions. Okay, so it looks a bit like wire, right? So like electrical wires. So we have quick, fast transmissions through the nervous system. So these signals going through from the brain, spinal cord, and into the nerves is quick, and it allows quick response to any changes in temperature. So there's thermoreceptors, the hypothalamus. So the thermoreceptors are the sensors, and they sense the change. The hypothalamus is our control, and our effectors like sweat glands and blood vessels get information from our nerves that come back and tell them to start working. So we are, looking at the world around us. We can feel that it's getting hot, and we're getting too hot, we're getting too cold. And so our nervous system kicks in really quickly so that we can get back to normal very quickly, and that we're not going to basically cook because it's too hot. If you have a look here, we have our thermoreceptors, which are in our skin, inside in our organs. So that's what our visceral temperature is. Our muscles, our heart, our glands, everything like that is taking in all of this information, going, am I at the right temperature? Am I too cold? Am I too hot? So all of these things in our body then send those signals back to the brain and says, we're too hot or we're too cold. And that then sends very quick responses down to the blood vessels to make sure that they dilate, our sweat glands so that we start to sweat. Our breathing might increase as well to try and breathe off some of that hot air, and that hopefully cools us down. On the other hand, if those receptors in our body are going on too cold, then our hypothalamus sends messages out to the blood vessels to constrict, to get smaller, and the muscles start to shiver and hormones start to be released. This is so that it's very quick and we can change our temperature quite quickly. Here is another diagram to help you understand this. It does look very busy, but stick with me. And if it's too much and you don't learn like that, that's fine as well. Just move onto a different section that explains it differently. So we have when you get too hot at the top, and you've got when you get too cold at the bottom. So the imbalance here, so the stimulus will be your body temperature is getting too high. So potentially you've been exercising, you're starting to get a bit hot, or it's 45 degrees outside and you're playing cricket and you're standing in the sun, right? So your blood then gets hotter because your body is getting hotter. And those thermoreceptors that we talked about in your body are going to sense that, and it sends a message up to hypothalamus in the brain. It says, we're getting way too hot. The brain then sends messages back to our blood vessels and our sweat glands so the sweat glands are activated, so we start to perspire and it evaporates, or the blood vessels now dilate, get bigger and get close to the skin surface. That's why we get flushed, so that some heat can come out of our body. Body temperature then decreases. This is our response, and it sends a message back to the brain going, we're good now. And so that hypothalamus heat loss center shuts off and stops doing what it needs to, stops cooling the body. other way around, the stimulus here, the decreased body temperature. So for example, you're in wet clothes and you've been lying in wet clothes for too long and you get too cold, or you get stuck in a snowstorm, which is unusual in Australia, but it could happen. So now blood becomes cooler than what it should be, and so the thermoreceptors pick that up and send a message to the brain and saying we're too cold. And so now our skeletal muscles get a message from the brain saying we need to start shivering and moving to get some heat going, and the blood vessels constrict, moving blood away from the skin so that we don't lose heat from there, but also to help all our insides and important parts, so our brain, our heart, our lungs, to have good blood flow, and keeps the warm blood inside. And then our body temperature hopefully goes back up and the hypothalamus gets told, yep, we're good now, stop going. All right, so the endocrine system. So remember, the endocrine system releases hormones. So we've got lots of different glands. We've got our thyroid, we've got our adrenal glands, we've got our sex organs that release hormones, all of that. And these hormones go directly into the bloodstream and they travel around to our organs and tissues and allow us to have a response. This allows maintaining homeostasis with the nervous system, but remembering that this is a little bit slower than the nervous system. So the nervous system is that immediate response, and this is more of the long-lasting response. So often the endocrine system is in charge of things like growth and development and metabolism, but it can also help our energy levels, our temperature regulation, by acting over extended periods, so that we don't just get back to normal temperature and then it's still 45 degrees outside and we just get hot again as soon as the hypothalamus turns off. Okay, so this allows us to maintain what's normal over a long period of time. And it works together well with the nervous system. So for example, there are hormones that, like adrenaline. So when you see a saber-toothed tiger and you need to run away, the adrenaline is released and it helps to increase your metabolic rate and gets your muscles ready to go and you can run away. But things like thyroxine as well, this also influences our metabolic rate. So sometimes we talk about that like our metabolism, but it's basically how fast our body is doing all its things, how fast it's processing our food, how fast it's growing. So the hypothalamus can also tell our thyroid gland to release some thyroxine, which then increases our metabolic rate. And because it's working harder, the body's working harder, it produces heat. And that then sends back to our skin and goes, okay, we're getting warm now. The thermoreceptors go, okay, we're good now. And it kind of regulates over time. All right. Now, this is just a quick review of how the nervous system is quick and the endocrine system is a little bit of a long-term thing.
Chemicals called neurotransmitters travel across synapses to encourage or discourage cellular responses.
So that's nice and quick, a bit like electricity.
Hormones dissolve in the bloodstream and circulate through many tissues. Each hormone will bind only to matching receptors on target cells. The binding triggers actions that alter the behavior of cells and tissues, as well as whole body functions.
So you can see that the hormones take a little bit longer to get to where they need to go, but they last longer, whereas the nervous system is very quick. It happens almost instantaneously. Okay, so now we know that the nervous system and the endocrine system work together to maintain our temperature. But what happens if it can't maintain it and it starts to fail? What's going to happen in our bodies? So we have something called heat stroke, and we've got something called hypothermia. Now, you might have heard the word heat stroke or heat exhaustion, but basically if the body is trying to cool down itself and it just can't, and it keeps getting hotter and hotter and hotter, eventually the nervous system can't keep up. So the sweat glands can't keep going. The endocrine system might not produce enough adrenaline and increase blood flow to the skin, so we can't then release heat from our skin. And then our brain starts to shut down and we actually get quite unwell. Now I'm going to show you a little clip of the difference between heat stroke and heat exhaustion.
Heat stroke kills up to 30% of the people that have it. But most people say they have heat stroke when they actually have heat exhaustion. Heat exhaustion is when you have a temperature between 37 and 40 degrees Celsius, and you may have a high heart rate, you might be sweating, you might be a little lightheaded. But the important difference here is you can think straight. Heat stroke is when you have a temperature of 40 degrees Celsius, which is 104 degrees Fahrenheit, plus you have a neurologic abnormality, confusion, slurred speech, coma, seizures. Both need to go to the ER because you can have severe electrolyte abnormalities, even if it's just heat exhaustion. But for heat stroke, you need to jump into action immediately. Call the ambulance, but don't wait for the ambulance to get there. Throw your friend in a bath with cold water, dump as much ice in there as you have. Share this with a friend to stay safe this summer, and follow up for more medical tips.
You'll see there that with heat stroke, they don't actually sweat. And that's because now the body can no longer send messages from the brain to our sweat glands to sweat. And so we just keep getting hotter and hotter and hotter. All right, now I'm going to show you one about hypothermia, which is low.
As your temperature drops, your body and brain fire back. Your thyroid and adrenal glands release a flood of hormones that boost your metabolism, heart rate, and blood pressure. In the brain, the hypothalamus tells your blood vessels to constrict. This moves the blood further from the skin's surface where heat can escape. Your hypothalamus also signals your muscles to shiver, which kicks your metabolism into overdrive 2 to 5 times the normal rate. At this point, you're on the brink. If you don't get to safety soon, you'll hit severe hypothermia and be in serious trouble. Eventually, even your brain will grow colder. When this happens, it stops functioning properly, which can make you feel dizzy, disoriented, and even want to strip naked. Before too long, you'll run the risk of permanent brain damage. But just how long do you have? It's hard to know because each situation and person is completely different.
The main point of today is that the nervous and endocrine systems collaborate intricately to maintain a good balanced temperature around about 37 degrees Celsius. They detect temperature changes through thermoreceptors. They then send messages from the brain to nerves, blood vessels, muscles, all of that, sweat glands, to help us maintain. We then have our thyroxine, our adrenaline, and all of that as well to assist the nervous system. If they don't work, or they get overloaded, so they've been trying and trying and trying to adjust the body temperature, but we're still sitting outside in the sun for too long, or we're still sitting in a snowstorm, eventually it's going to fail, and then we're no longer able to do these things that help bring our temperature back to normal, and we can be quite unwell. So last thing I would like you to do for the lesson today is, in your journals, I would like you to do a little self-reflect and assess. And this is just to help determine where you're at, determine any gaps in knowledge, and I would like you to let me know, especially number 2. Okay, so first one, what did I learn about how my body maintains temperature? Okay, so anything that you learned today that you didn't know before. And number 2, what part of the feedback loop was hardest to understand? Now, this one I would like you to share with me. So I will set up a little Padlet and you can attach onto that. And one real world example of thermoregulation I can explain is, so again, pick and choose whatever you'd like. So the first one and the third one are for your learning, and the second one I'd like to help you with that so that we can cover some gaps next lesson. But thank you for your attention. I hope that you have a bit more understanding of thermoregulation and how that works with the nervous and endocrine system. And I look forward to seeing you for the last lesson of this little topic coming up next. Bye.